Hello there, and welcome to Astral Lab, where we investigate the strangest open questions in modern science, one careful step at a time. Tonight, we're going to examine something that sounds like science fiction, but is actually being studied seriously by working physicists right now. The kind of question most people assume has only one possible answer. The kind that science fiction has been borrowing for nearly a century. The kind that, when you look at the actual research literature, turns out to be one of the most genuinely unresolved problems in 21st century physics. Have scientists actually found a real way to travel faster than light? Now, if you have ever watched a science fiction film or read a science fiction novel, faster than light travel might feel like a permanent fixture of imagination. Spaceships casually crossing galaxies in hours. Warp drives humming politely in the background. Distances that should take hundreds of thousands of years collapsed into a brief montage between commercial breaks. But the actual situation in physics is far stranger than that. There is a hard wall built into the universe at the speed of light, and for 100 years, scientists believed it was absolutely unbreakable. Then, in 1994, a Mexican physicist sitting in Cambridge published a short paper that quietly rewrote that belief, not by breaking the wall, but by going around it. Since then, the question has refused to go away. So tonight, we will walk through the entire investigation. We will work through why every rocket humans have ever built fails completely at the scales we are actually talking about. What Einstein really meant when he said nothing can travel faster than light. The strange loophole hidden inside the expansion of the universe itself, the 1994 paper that changed everything, and the genuinely surprising research happening right now in laboratories that may or may not be inching towards something nobody thought was possible. Along the way, we will meet a physicist who measured negative energy in a basement, an experimental researcher at NASA who built a small device and watched the math do something strange, and a German physicist who, in 2021, published a result that several of his colleagues thought was either revolutionary or completely wrong, depending on which colleague you asked. The investigation does not produce a tidy ending, but it produces a real one, and the answer to the title question turns out to be more interesting than either yes or no. But before we begin, I would like to know something simple. Where are you listening from tonight? And what time is it in your corner of the world right now? Perhaps it is late evening. Perhaps it is raining. Maybe you are already half wrapped in blankets, wondering how a question about faster-than-light spaceships somehow became tonight's bedtime destination. It is, admittedly, a slightly unusual choice. Still, if you find these long, careful investigations into the strange edges of physics interesting, I would be genuinely grateful if you like the video and maybe subscribe as well. It helps Astral Lab keep finding the quiet corners of physics that do not usually make it into the headlines. The corners where physicists are still arguing in journal papers about whether something is possible instead of certain. And honestly, that quiet disagreement is part of the reason this story is so interesting. The history of faster-than-light research is not a history of dramatic breakthroughs and triumphant announcements. It is a history of careful papers, gentle disagreements, slow refinements, and a small number of moments where the math did something nobody quite expected. The wall is still there, but the conversation around the wall has become surprisingly serious. So, settle in. The investigation is going to take a while. And with that, let us begin. The wall is closer than you think. Let us start with the problem, because before any conversation about faster-than-light travel can make sense, you have to understand exactly how impossible the situation is using ordinary physics. And it is not impossible in the sense of difficult or expensive or technologically out of reach. It is impossible in a much deeper way. The kind of impossible that holds even after you remove every practical limitation you can imagine. Picture the nearest star system to our own. It is called Proxima Centauri, and it sits a little over 4 light-years away. 4.24 light-years to be precise. Now, that number sounds manageable. 4 of anything tends to feel like a reasonable amount. 4 apples, 4 hours, 4 days, even 4 years has a familiar shape to it. So 4 light years initially sounds like it might be a long trip, but not an unimaginable one. The trouble is that light years are not normal units. A light year is the distance light travels in a year. And light travels at almost 300,000 kilometers every single second. So in 1 year, light covers roughly 9.5 trillion kilometers. Multiply that by 4.24 and you get a number with 13 digits in front of the decimal point. That is the distance to the nearest star. To make that number feel like anything other than abstract arithmetic, it helps to compare it to something familiar. The fastest spacecraft humans have ever launched away from Earth is Voyager 1. It left in 1977, has been moving outward without a break for almost half a century, and is currently traveling at roughly 17 kilometers per second. At that speed, if Voyager 1 were aimed at Proxima Centauri and given a clear straight path, it would take approximately 73,000 years to arrive. Not 700, not 7,000, 73,000. Roughly the length of time since the last ice age was at its coldest point. If our distant ancestors had launched a Voyager probe at the end of the last glacial maximum, it would still be travelling toward Proxima Centauri today, with another 20,000 or so years remaining on the journey. There is something else worth noting about that 73,000-year figure, because it actually understates the problem in a subtle way. Voyager 1 did not start its journey from a standing stop. It was launched by a Titan rocket from Earth, given gravitational assists from Jupiter and Saturn, and then released into deep space carrying the accumulated speed of all those maneuvers. Most of its current velocity was acquired during those flybys, not by any onboard propulsion. The probe itself does not have a working engine for course corrections anymore. The fuel is essentially gone. Voyager is coasting outward at the speed it had decades ago, and it will continue to coast at roughly that speed for the rest of its existence, because there is nothing in interstellar space to slow it down. So when we talk about Voyager taking 73,000 years to reach Proxima Centauri, we are talking about the upper limit of what current technology can actually achieve in terms of sustained interstellar speed, not the lower limit of what it could do given better engines. That comparison sometimes lands harder than the raw numbers, because human history simply does not have categories large enough to absorb interstellar distances. Most of the things we think of as ancient, the pyramids of Egypt, the cave paintings at Lascaux, the first agricultural settlements, are all only a few thousand years old. A trip to the nearest star using our fastest current technology would take longer than every civilization, every empire, every recorded language, every war and treaty and king and queen in human history, repeated more than 10 times back to back. The other piece of context worth holding is that Proxima Centauri is not, in any meaningful sense, an interesting destination. It is the closest star to our own, but it is a red dwarf much smaller and cooler than the Sun and the one known planet in its system called Proxima b. Sits in an orbit so close to its parent star that it is probably tidally locked with one side permanently facing the star and the other permanently in shadow. The radiation environment around a red dwarf is generally hostile to anything resembling Earth life. The flares are large. The ultraviolet output during those flares is extreme. The conditions on the planet are not what most people imagine when they imagine a destination worth traveling 73,000 years to visit. So the actual target for any serious interstellar mission would more likely be a star further out, with a more sun-like profile and a planet in a more clement orbit, which means the relevant distance for thinking about practical interstellar travel is not 4.24 light-years. It is more like 10 or 20 or 50 light-years depending on which star you pick. The numbers, in other words, are even worse than the headline figure suggests, and here is the part that tends to disturb people when they first encounter it. Proxima Centauri is the closest star. The galaxy contains roughly 200 billion stars. Many of them sit thousands or tens of thousands of light-years away. Some sit 100,000 light-years away on the opposite side of the Milky Way. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. Even the most aggressive imagination tends to give up somewhere around the second comma in those numbers. And there is one more piece of perspective that occasionally helps. Light from Proxima Centauri left that star 4.24 years ago. So when you go outside on a clear night and look toward the constellation Centaurus, the photons reaching your eyes from Proxima are arriving after a 4-year journey through interstellar space. The star itself, as it exists in this moment, might already be different from the version your eyes are seeing. You are looking at a slightly out-of-date image, delayed by the time it takes light to cross even that closest of interstellar distances. So when we talk about whether scientists have found a way to travel faster than light, what we are really asking is whether there is any path that makes interstellar travel a remotely sensible idea on human timescales. Not the scale of generations sealed inside a slow generation ship. Not the scale of frozen embryos arriving in a 1,000-year capsule. Something closer to the kind of trip a human being could realistically begin and finish within a single lifetime. And to do that, you need to confront the wall. The wall, as physicists understand it, is the speed of light itself. And we will spend the next 20,000 words walking around it slowly, looking at it from every angle, until you understand exactly what it is and what, if anything, can be done about it. Why? Every rocket humans have ever built cannot save us. Before we get to the wall itself, we need to understand exactly why ordinary engineering cannot solve this problem. Because the obvious response to a long trip is to build a faster ship. That is what humans have always done. The history of transportation is essentially the history of getting faster. Horses gave way to trains. Trains gave way to cars. Cars were joined by aircraft. Aircraft were joined by rockets. Each generation looked at the previous one and found ways to compress the distances that used to define it. And it is reasonable to assume the pattern will continue, at least until physics stops cooperating. The trouble is that physics, in the case of interstellar travel, stops cooperating almost immediately. The reason has to do with a mathematical relationship called the rocket equation, which was worked out by a Russian schoolteacher named Konstantin Tsiolkovsky in the early 1900s. The equation itself is not particularly intimidating to look at, but the conclusion it forces is genuinely brutal. The faster you want a rocket to go, the more fuel you need to carry. And because that fuel itself has mass, you also need extra fuel to accelerate the fuel, which means you need even more fuel to accelerate that fuel. And so on, in a way that compounds exponentially rather than linearly. It is worth dwelling on the rocket equation for a moment longer, because it is one of those rare physical relationships where the conclusion is genuinely worse than the intuition. Most physical limitations scale linearly. If you want to do twice as much work, you need roughly twice as much energy. The rocket equation does not work that way. The relationship between target speed and required fuel mass is exponential, which means that small increases in target speed produce enormous increases in fuel requirement. Doubling the target speed of a rocket using a given propellant does not require twice as much fuel. It requires the original fuel mass squared, or close to it, depending on the specifics. This is why every rocket ever launched has been almost entirely fueled by mass, with the actual payload making up only a tiny fraction of the launch vehicle. The Saturn V that took the Apollo astronauts to the moon was about 94% fuel at launch. To go meaningfully faster than that, the fraction has to climb even higher, until you are essentially building a tank of fuel with a payload glued to the top, and then the equation eats even that thin payload. In practical terms, this means that even very modest target speeds require absurd ratios of fuel to payload. A rocket designed to reach a tenth of the speed of light using ordinary chemical propulsion would have to be made almost entirely of fuel, with a payload smaller than a paperclip relative to the launch mass. That is not an engineering limitation. It is a mathematical one. You cannot fix it by being clever about the rocket's shape, or by building lighter materials, or by optimizing the trajectory. The equation simply does not allow it. The way around the rocket equation, in principle, is to use propellants that release energy at a much higher rate than chemical combustion. This is what nuclear pulse propulsion, ion drives, and antimatter rockets are all trying to do. They use exotic energy sources to produce much higher exhaust velocities, which lets you get more thrust per unit of fuel mass. The improvements are real but bounded. Ion drives can reach exhaust velocities 10 or 20 times higher than chemical rockets, which is genuinely significant. Antimatter, if it could be produced and stored in usable quantities, could in principle approach the speed of light in its exhaust, which would offer the best possible performance under the rocket equation. But antimatter today can only be produced in particle accelerators at rates of nanograms per year, at costs estimated in the billions of dollars per gram, with no current technology for storing it safely. The path forward, even using exotic propellants, narrows to nothing well before you reach speeds that matter for interstellar travel. Engineers have, of course, tried to escape the equation by inventing fundamentally different forms of propulsion. The most famous attempt was a project called Orion, proposed in the late 1950s and worked on seriously by a team that included the physicist Freeman Dyson. The idea, which sounds vaguely like a practical joke until you read the actual papers, was to propel a spacecraft by detonating a sequence of small nuclear bombs behind it. The bombs would be released one at a time, exploding against a heavy pusher plate at the back of the ship. Each explosion would transfer momentum forward. With enough bombs, the ship could, in principle, accelerate to a meaningful fraction of light speed. The Orion calculations actually worked, on paper. Project members performed small-scale tests using conventional explosives and found that the basic physics held up. The political and environmental problems with detonating thousands of nuclear devices in the atmosphere, however, were what you might expect, and the project was eventually abandoned. Even if it had been built, it would have produced speeds of around 3 to 10% of the speed of light, which is impressive, but still means a journey to Proxima Centauri lasting 40 years or more. Not a single human lifetime, not anything resembling a casual trip. Other engineering approaches face similar problems. Ion drives, which use electric fields to accelerate charged particles, can reach high speeds eventually, but their thrust is so weak that they take years to build up to meaningful velocities. They are useful for unmanned probes within the solar system, but completely impractical for crewed interstellar missions. Solar sails, propelled by the pressure of sunlight or by ground-based lasers aimed at reflective surfaces, can in principle reach very high speeds, but only for tiny payloads. The Breakthrough Starshot project, proposed in 2016, is worth understanding in a bit more detail because it represents the most aggressive serious proposal for an actual interstellar mission. The plan, sketched out by a consortium including Yuri Milner, Stephen Hawking, and Mark Zuckerberg, involves building a ground-based laser array in the Atacama Desert of Chile. The array, when complete, would be capable of producing a coordinated laser pulse of roughly 100 gigawatts, briefly making it the most powerful light source ever constructed. The laser would target small spacecraft, each weighing around 1 gram and equipped with a thin reflective sail roughly 4 meters on a side. The pulse would accelerate the sails to about 20% of the speed of light over the course of a few minutes, at which point they would coast across the gap to Proxima Centauri, arriving in roughly 20 years. The probes would have no way to slow down at the destination, no way to do significant science beyond a brief flyby, and no way to return data with a useful signal-to-noise ratio. But they would, in principle, arrive. And this is the situation. Even the most aggressive engineering proposals, the ones that involve detonating nuclear weapons or accelerating chips of silicon with industrial-scale lasers, top out at roughly 10% of the speed of light. To get a meaningful interstellar mission, with a real crew or a substantial cargo, on a timescale that means anything to human beings, you would need to get much closer to the speed of light itself. And that is where the engineering problem stops being an engineering problem and becomes something fundamentally different. Because as you approach the speed of light, the universe itself starts to push back. The wall is not made of fuel limits or material strength. It is built into the structure of space-time itself. And, to understand what that means, we need to talk about the man who first wrote down the wall's equations, Einstein's wall, and why it is not what you think. In 1905, an unknown patent clerk in Switzerland published 4 papers that quietly rearranged the foundations of physics. The clerk was Albert Einstein, and one of those papers introduced what we now call special relativity. Among many other things, special relativity contains a statement that has become so famous it now feels almost decorative. Nothing can travel faster than the speed of light. That statement is true. It is also widely misunderstood. Most people, when they first encounter it, imagine that the speed of light is something like an extremely high speed limit imposed by the universe, the way a highway might have a posted maximum velocity. The intuition that follows is that with enough power, enough technology, and enough determination, you could, in principle, push past it. That intuition is wrong, and it is wrong in a specific way that takes some patience to unwind. The speed of light is not a limit in the ordinary sense. It is something more like a fundamental geometric feature of the universe itself. To see why, you have to understand that in Einstein's framework, space and time are not separate. They are bound together into a single 4-dimensional fabric called spacetime, and motion through this fabric obeys rules that have very little in common with everyday experience. The faster an object moves through space, the slower it moves through time from the perspective of an outside observer. At low speeds, the effect is so small as to be undetectable. At speeds approaching that of light, the effect becomes dramatic. One way to get a better intuition for why the speed of light functions as a fundamental limit rather than merely a high-speed limit is to think about what would actually happen to a spacecraft that tried to approach it. As the spacecraft accelerates, several effects start to become important. Time, as measured by clocks on board the ship, runs slower compared to clocks on Earth. Lengths in the direction of motion contract from the perspective of outside observers. The mass of the ship, in the sense relevant to its resistance to further acceleration, increases. None of these effects are illusions or artifacts. They are real and have been confirmed experimentally in particle accelerators, where individual particles are routinely accelerated to within a fraction of a percent of light speed. The effects scale in exactly the way special relativity predicts, and the energy required to push a particle from 99% of light speed to 99.9% of light speed is much larger than the energy required to push it from 0 to 90%. The closer you get to the limit, the steeper the climb. Now here is the strange part. If you try to accelerate a massive object closer and closer to the speed of light, you discover that pushing it faster takes more and more energy. Not in a linear way. In a way that climbs steeply as you approach the limit. At 90% of the speed of light, the energy required to gain a single additional kilometer per second is already enormous. At 99%, it is staggering. At 99.9%, it is absurd. And as you approach the speed of light itself, the energy required approaches infinity. That is the wall. It is not a wall that pushes back when you hit it. It is a wall built out of the cost of every additional meter per second. The closer you get to the speed of light, the steeper the cost grows. And to actually reach the speed of light, you would need infinite energy, not a very large amount. Infinite, which is a polite way of saying it is not going to happen. The universe simply does not have that much energy. The total energy of every star in every galaxy in the observable universe is finite. And finite numbers, no matter how enormous, are not infinite. This is why physicists describe the speed of light as a fundamental limit rather than an engineering challenge. It is not that we have not built a powerful enough engine, it is that no engine, of any conceivable design, using any conceivable fuel, can deliver the energy required. The wall is built into the geometry of the universe. The speed of light is the maximum speed at which any signal, any particle, any influence of any kind can move through spacetime. Everything that has mass is permanently locked below this limit. Everything massless, like light itself or other photons, travels exactly at this limit. Nothing travels above it, not because we lack the tools, because the geometry does not allow it. The other detail worth understanding is that the speed of light is not just a limit on motion, it is also the maximum speed at which any influence can propagate through the universe. This means that no signal, no message, no causal effect can move from one point to another faster than light. If something happens at one end of the galaxy, the news of that event cannot reach the other end faster than the time it takes light to cross the distance. This is sometimes called the principle of locality, and it is one of the most strictly enforced rules in physics. Every successful theory we have ever developed obeys it. Every experiment ever conducted has been consistent with it. The speed of light, in this sense, is the speed at which the universe updates itself. It is the speed of causality. Nothing can be faster than that, because faster means before, in the sense of preceding the cause, which the universe does not permit. And here is the strange consolation that hides inside this picture. Einstein never actually said that nothing can travel faster than light. What he said, very precisely, is that nothing with mass can be accelerated through space faster than light. That is a careful sentence. It applies to objects moving through space. It does not necessarily apply to space itself. And that distinction, which sounds at first like a piece of legal hair-splitting, turns out to be the loophole that the entire rest of this investigation walks through. The loophole that hides inside, the expansion of the universe. Now we come to the strangest part of the setup, and the part that almost nobody outside physics knows about. Space itself can move faster than light. It happens all the time. It is happening right now, in fact, in regions of the universe so distant that the light from those regions will never reach us. To understand how this is possible without violating Einstein's wall, you have to remember the careful sentence from the end of the last section. Nothing with mass can be accelerated through space faster than light. The qualifier through space is doing serious work in that sentence. It refers to objects moving from one position to another within the fabric of space-time. The wall applies to that kind of motion, but the fabric itself is not bound by the same rule. Space can stretch, expand, compress, or warp. And when it does, the things sitting inside it can be carried along at speeds that, measured against distant observers, exceed the speed of light without anybody actually accelerating anything. This sounds at first like a piece of physics trickery, the kind of fine print that exists more in textbooks than in the real universe. But it is not a trick. It is the actual situation in the cosmos right now. The universe has been expanding since the Big Bang almost 14 billion years ago, and the expansion is happening at a rate that depends on a quantity called the Hubble constant. The further away two points are from each other, the faster the space between them stretches. At sufficiently large distances, the space between two galaxies stretches faster than light can travel across it. The galaxies themselves are not moving faster than light through space. The space between them is simply expanding, and the cumulative expansion adds up. The expansion of the universe is worth understanding in slightly more detail, because it is a piece of physics that most people have heard of without having had a chance to think about carefully. The universe has been expanding since the Big Bang. This means that, on the largest scales, galaxies are moving apart from each other. The expansion is not happening because galaxies are propelling themselves outward. Galaxies are essentially stationary relative to their local patch of space. The space itself is stretching, and the galaxies are being carried along with it, the way raisins might be carried apart by a rising loaf of bread. The further apart two raisins are, the faster they separate, because there is more bread between them that is rising. The mathematics is the same for cosmological expansion. The further apart two galaxies are, the faster the space between them expands, because there is more space between them to expand. This effect was first measured by the American astronomer Edwin Hubble in the 1920s, using observations of distant galaxies made at Mount Wilson Observatory in California. Hubble noticed that the light from distant galaxies was redshifted, meaning its wavelengths had been stretched into longer ones. The further away a galaxy was, the larger the redshift. He interpreted this correctly as evidence that the galaxies were moving away from us and that the speed of recession was proportional to distance. The relationship became known as Hubble's law, and the constant that describes it, the Hubble constant, has been measured with increasing precision over the last century. Current measurements give a value of roughly 70 kilometers per second per megaparsec, where a megaparsec is about 3.3 million light-years. This means that for every megaparsec of distance, the recession speed adds about 70 kilometers per second. There is a specific name for the distance at which this effect becomes total. It is called the Hubble radius, and it sits at roughly 14 billion light-years from any observer. Beyond that distance, space recedes from us faster than light can cross it, which means light emitted by galaxies beyond the Hubble radius will never reach us. They are not gone. They are not destroyed. They are simply, from our perspective, locked permanently away by the expansion of the space between us. Now here is the thought that physicists in the late 20th century started taking seriously. If space itself can expand faster than light without violating any laws, then in principle, space itself could also contract faster than light without violating any laws. And if space can be made to contract in front of a spacecraft while expanding behind it, the spacecraft could be carried forward at any speed, including effective speeds far greater than that of light, without ever locally moving faster than light through any patch of space. The picture that emerges from this idea is genuinely strange. Imagine you are sitting in a small chair and the chair is not moving. Now imagine that the floor in front of the chair is being pulled toward you, while the floor behind the chair is being pushed away. The chair itself, locally, is stationary. You feel no motion, no wind in your hair, no acceleration pressing you against the back of the seat. But the room you are in, considered as a whole, is sliding across the ground. From the perspective of someone standing outside the building, you are moving at whatever speed the floor is being manipulated at. From your perspective inside the chair, nothing is happening at all. That, in extremely rough sketch, is the idea behind every serious proposal for faster-than-light travel in modern physics. You do not push the ship through space. You manipulate the space the ship is sitting in. The ship itself never accelerates. The wall is never crossed. And yet the ship arrives at its destination far sooner than light would have because the geometry of space around it has been temporarily rearranged. That is the loophole. It sounds preposterous when you first hear it. But it is not science fiction. It is a direct consequence of the geometry that Einstein himself worked out 100 years ago. The only question is whether such a manipulation of space could actually be carried out in practice. For most of the 20th century, the assumption was that the answer was a quiet but absolute no. The mathematics of general relativity certainly allowed strange things, but they were generally assumed to be mathematical curiosities with no physical realization. That assumption held until 1994. When a young Mexican physicist sitting at Cambridge published a paper that nobody quite knew what to do with. 1994, Cambridge, a Mexican physicist. The paper appeared in the journal Classical and Quantum Gravity in May of 1994. It was 8 pages long, which is short by the standards of physics papers. Its title was technical and slightly unassuming. It read, "The Warp Drive, Hyperfast Travel Within General Relativity." The author was Miguel Alcubierre, a Mexican theoretical physicist who had recently completed his doctorate at the University of Wales and was working at the time on questions involving numerical relativity. He was, by his own later account, watching an episode of Star Trek when the idea first occurred to him, which is, admittedly, a very honest origin story for a physics paper. The basic idea Alcubierre proposed was elegant in a way that good physics ideas sometimes are. He asked a simple question. Was there any solution to Einstein's equations of general relativity that would allow a spacecraft to travel between 2 distant points faster than light without violating the local speed limit at any individual point along the way? In other words, was there a way to write down a geometric arrangement of space that delivered the effect of faster than light travel, even though no part of the geometry itself involved anything moving faster than light? And, to his apparent surprise, the answer turned out to be yes. The geometry Alcubierre described had a specific shape. It was a small region of space-time, shaped roughly like a bubble or an envelope, in which space itself was being actively manipulated. In front of the bubble, space was being contracted, squeezed inward. Behind the bubble, space was being expanded, pushed outward. Inside the bubble, a flat region of normal space-time sat motionless. A spacecraft placed inside this flat interior would, from its own perspective, not be moving at all. But the bubble as a whole, considered against the background of distant stars, would slide forward at any speed the contraction and expansion rates allowed, including speeds far greater than that of light. The crucial feature was that the spacecraft itself never accelerated. It sat inside a calm pocket of space-time where the local physics looked completely ordinary. There was no enormous engine, no fuel being burned, no relativistic mass increase, no time dilation in the usual sense. Inside the bubble, life went on at normal speed. Outside, space did the work. The wall that Einstein had built into the universe was not violated. It was simply walked around. There is one more biographical detail about Miguel Alcubierre that is worth knowing because it humanizes the story in a useful way. Alcubierre did not set out to invent a warp drive. He was working, at the time, on questions involving numerical simulations of black hole collisions, which was a difficult and demanding area of computational physics. The warp drive paper was, in his own description, a side project, the kind of thing you do in the evenings or on weekends when the main research is going slowly. He has said in interviews that he wrote the paper partly as an exercise, to see whether the mathematics would work, and that he was as surprised as anyone when it did. He went on to a distinguished career in theoretical physics, holding senior positions at the National Autonomous University of Mexico, and he has continued working on numerical relativity and related questions. The warp drive paper is now, by a substantial margin, the most cited piece of work he ever produced, but it is not what he considers his main scientific contribution. The Starship community claimed him, somewhat against his own preferences. It is also worth being precise about exactly what Alcubierre's paper does and does not say. The paper does not claim that a warp drive can be built. It does not claim that the warp drive is physically realizable. It does not claim that exotic matter exists in nature in usable quantities. It claims, very specifically and very carefully, that there is a valid solution to Einstein's equations that has the geometric properties of a warp bubble. That is all. The interpretation of that mathematical solution as a possible engineering project is something that other people, often without Alcubierre's caution, have done in the years since. The paper itself is a piece of pure theoretical work, and the conclusions it draws are correspondingly modest. It says, in effect, the mathematics permits this geometry. Whether the universe permits this geometry to be built is a separate question. When the paper appeared, it produced a strange mixture of reactions in the physics community. The mathematics was clean. The solution genuinely was a valid solution to Einstein's equations. There was nothing about it that could be dismissed as a mistake or an error. At the same time, the implications were so unusual that nobody quite knew how seriously to take it. Was this a real physical possibility? Or was it a mathematical curiosity, the kind of thing the equations technically allowed, but the universe would never actually realize? To understand what was at stake, you have to understand that general relativity, the theory that governs the geometry of space-time, allows for an enormous range of mathematical solutions. The equations are flexible. They permit black holes, wormholes, cosmic strings, expanding universes, contracting universes, and a wide variety of other exotic configurations. The question, in each case, is whether the configuration can actually be built in the universe we live in. Many solutions require ingredients that turn out to be physically impossible. The equations allow them, but the laws of physics elsewhere in the theoretical landscape do not. Alcubierre's warp bubble was a valid mathematical solution. That part was not in dispute. The question was what it would take to actually build one. And when physicists started working through the requirements, the answer turned out to be alarming. To produce the kind of space-time distortion the bubble required, you needed an exotic kind of matter. Not ordinary matter. Not exotic in the loose sense of unusual or expensive. Exotic in the technical sense, meaning matter with negative energy density. Material that pushed outward instead of inward, that resisted gravity instead of producing it, that behaved in ways that no substance in the known universe behaves. And the amount of this negative energy material required, by Alcubierre's original calculations, was enormous. The figure quoted in the paper was the mass equivalent of an object roughly the size of Jupiter. Not Jupiter's mass exactly, but a quantity of negative energy that, expressed in equivalent ordinary mass terms, came out to that scale. The reaction in the physics community was, roughly, that the paper was beautiful and clever, but also probably useless. You could write down a warp drive on paper, you could not build one, and so the warp drive joined the long list of mathematical curiosities in general relativity that the universe technically allows but practically forbids. For about a decade, the story went quiet. Then, slowly, something interesting started happening. Other physicists began looking at the original Alcubierre paper and asking whether the numbers really had to be that bad. Maybe the bubble geometry could be adjusted to require less negative energy. Maybe the assumptions could be relaxed. Maybe the impossible could be reduced to merely the extremely difficult. And once that question started getting asked seriously, the warp drive stopped being a curiosity and started becoming a research program. The wall had not moved. But the conversation about the wall had quietly changed shape. The catch that stopped the celebration. Before we follow the thread of refinements that physicists made to Alcubierre's drive, we need to understand exactly what made the original version impractical. Because the story of the next 30 years of warp drive research is essentially the story of physicists trying to shrink one specific number. And to understand why that number matters so much, you have to understand what negative energy actually is, and why the universe makes it so difficult to obtain. In ordinary physics, energy is always positive. A moving object has positive kinetic energy. A stretched spring has positive potential energy. The light from the sun carries positive energy across space to warm the surface of the Earth. Even the vacuum of empty space, in modern quantum theory, is filled with a tiny positive baseline energy called the zero-point energy. Everywhere you look, in every situation you can construct, the energies you measure come out positive. This is not just an empirical fact. It is built deeply into the structure of the theories we use to describe the universe. There is a deeper reason why negative energy is so difficult to obtain in the universe, and it is worth understanding because it tells us something important about the structure of physical law. In standard quantum field theory, the framework that describes the behavior of matter and energy at the smallest scales, the energy of any physical system is bounded below by zero. This is not an accident or an empirical observation. It is built into the mathematical structure of the theory in the form of conditions on the operators that describe physical quantities. Negative energy states, in standard quantum field theory, do not exist except in extremely specific configurations, like the Casimir effect that comes up later in this investigation. The universe does not provide them as a generally available resource. To get negative energy in any meaningful quantity, you have to construct very specific arrangements that exploit subtle features of quantum mechanics, and even then the amounts you can produce are tiny. Negative energy, by contrast, is something that the equations of general relativity allow as a possibility, but that almost never actually appears in nature. The handful of situations where it does appear are very strange and very specific, and we will get to them later in the investigation. For now, the relevant point is that you cannot just build a battery full of negative energy by stacking ordinary materials together. There is no chemical reaction, no engineering trick, no manufacturing process that produces it. To get a significant amount of negative energy, you would need a source that does not exist anywhere in the known universe, and the warp drive needs that source. The contracted space in front of the bubble and the expanded space behind it can only be produced by a substance that exerts negative pressure on the surrounding space-time. Ordinary matter does the opposite. It bends space inward, pulling things toward it. To push space outward, you need something that bends it the other way. And the only known mathematical description of such a substance involves negative energy density, which the universe does not appear to permit in large quantities. The figure Alcubierre originally calculated was that producing his bubble would require a quantity of negative energy, roughly equivalent to converting the entire mass of Jupiter into the exotic stuff. This was not an estimate. It was a direct consequence of the geometry he had written down. The shape of the bubble, the speed it traveled at, and the size of the protected interior region all combined to set a minimum negative energy requirement, and the answer came out at planet scale. To put the original Alcubierre energy requirement into context with something more familiar, consider that the total energy released by the most powerful nuclear weapon ever detonated, the Tsar bomber tested by the Soviet Union in 1961, was equivalent to about 50 megatons of TNT. That is a vast amount of energy in human terms. It was enough to flatten a city. Now consider that the negative energy required by the original Alcubierre drive, expressed in equivalent mass units, was roughly the mass of Jupiter. Jupiter has about 317 Earth masses worth of material. Converting all of that material into energy at the rate given by Einstein's famous mass-energy equation gives you something like 10 to the 44 joules. The Tsar bomber released about 2 times 10 to the 17 joules. The Alcubierre drive needed about 27 orders of magnitude more energy than humanity's most powerful weapon, and not just any energy, but a kind of energy the universe does not appear to provide in any normal way. To put this into further context, the total energy output of the Sun over its entire 10 billion year main sequence lifetime is roughly comparable to the rest mass energy of a few hundred Jupiters. So the negative energy required by the original Alcubierre drive was on the same order of magnitude as the energy output of a star over geological time, not an amount you could produce in a laboratory, not an amount you could produce on a planet, an amount you would need to harvest from astrophysical sources, assuming you had a way to convert positive energy into negative energy in the first place, which you do not. When this calculation became widely known, the immediate reaction in the physics community was that the warp drive was, for all practical purposes, dead on arrival. The mathematics was real. The mathematics was beautiful. But the engineering implications were so extreme that the result felt more like a piece of pure geometry than a piece of practical physics. It was, in the jargon, a no-go theorem in disguise. The drive existed in the mathematical landscape. It simply could not be reached from anywhere humans could realistically get to. But here is the part of the story that is interesting. The physicists who came after Alcubierre did not accept this verdict, not because they were optimists exactly, but because the original paper had assumed a particular shape for the warp bubble, and there was no obvious reason why that shape had to be the only one. The geometry of general relativity is enormously flexible. There are many different ways to arrange space and time to produce a similar effect. And the question that started to get asked, quietly at first and then more seriously, was whether a different bubble shape might require less negative energy, maybe much less, maybe enough less to bring the requirement down from planet scale to something more achievable. The mathematics did not forbid this question. It simply had not been explored. And in 1999, a Dutch physicist named Chris van den Broek decided to try. The engineer who made the bubble thinner, Chris van den Broek, was working at Utrecht University in the late 1990s when he published a paper that quietly transformed the warp drive conversation. The paper, which appeared in 1999 in the same journal that had carried Alcubierre's original work, asked a simple but pointed question. Was there a way to redesign the warp bubble so that the negative energy requirement, while still enormous, was at least no longer at planetary scale? And the answer, after Van den Broek had worked through the geometry, turned out to be yes. To understand what Van den Broek did, it helps to think carefully about the original Alcubierre bubble. In the 1994 paper, the bubble was relatively large, big enough to comfortably contain a sizable spacecraft inside its flat interior region. The wall of the bubble, the boundary between the protected interior and the manipulated exterior space, was also relatively thick. Both of these properties contributed to the enormous negative energy requirement. The larger the bubble and the thicker the wall, the more exotic matter you needed to maintain it. Van den Broek's insight was to ask what would happen if you decoupled the size of the bubble from the size of the spacecraft. In the original design, these two quantities were essentially the same. The bubble had to be at least as large as the ship inside it. But there is no fundamental rule in general relativity that requires this. You can, in principle, design a bubble that has a small exterior size, only a few meters across, but that contains a much larger interior region. The geometry of curved space-time allows this kind of bigger on the inside arrangement, in much the same way that the geometry of certain mathematical surfaces allows them to have more area than they appear to have when viewed from outside. The technique Van den Broek used to shrink the negative energy requirement is worth understanding in slightly more detail because it illustrates a general principle in modern physics that applies to many other problems. The principle is that when a calculation produces an answer that seems impossibly bad, it is often worth checking whether the calculation assumes something that did not have to be assumed. In the original Alcubierre paper, the assumption was that the warp bubble had to be a single contiguous region, with the spacecraft sitting inside the obvious flat interior. Van den Broek questioned this assumption. He asked whether the geometry could be configured so that the exterior of the bubble, as seen from a distance, was much smaller than the interior that the spacecraft actually occupied. The answer was that yes, the geometry allowed this, and the negative energy requirement scaled primarily with the exterior size rather than the interior. By making the exterior tiny while keeping the interior usable, the energy requirement dropped enormously. With this insight, Van den Broek constructed a modified warp bubble that had two distinct regions. The outer region, what you would see from a distance, was very small. The inner region, the actual flat interior where the spacecraft would sit, was much larger. The two regions were connected by a kind of geometric throat that allowed the interior to be expanded relative to the exterior. The exotic matter requirement, which depended primarily on the exterior dimensions of the bubble, dropped enormously. By Van den Broek's calculations, the negative energy needed could be reduced from the original Jupiter mass scale down to something closer to a few solar masses, and in optimized versions even lower. Now, a few solar masses of negative energy is still an absurd amount by any practical standard. The Sun, with its 100 million kilometer diameter and core temperatures of 15 million degrees, is not the kind of thing you can keep in a basement. So Van den Broek's paper did not solve the warp drive problem. It did not even come close. What it did was something more subtle and arguably more important. It demonstrated that Alcubierre's original number was not a fundamental limit. The Jupiter mass requirement was a consequence of a specific bubble design. Other designs could do better. The negative energy threshold was, in principle, negotiable. This may not sound like much, but in physics the difference between an impossible problem and a merely difficult problem is enormous. Before Van den Broek, the warp drive had looked like a piece of pure mathematics. After Van den Broek, it looked like an engineering problem with extraordinary requirements, but one where the requirements could potentially be reduced through clever geometry. The wall had not moved, but for the first time there was reason to think that the cost of going around it might not be a fixed number. Other physicists picked up the thread quickly. Throughout the early 2000s, a series of papers explored variations on the bubble design, each one finding ways to reduce the negative energy requirement further. Some involved making the bubble walls thinner. Others involved more sophisticated geometric arrangements that distributed the exotic matter more efficiently. The numbers kept coming down. Solar masses became stellar core masses. Stellar core masses became, in optimized versions, planet masses again, but now small planets rather than Jupiter. Some particularly aggressive proposals brought the requirement down to a few kilograms of negative energy if the bubble walls were made extraordinarily thin. Other refinements that followed Van den Broek's work explored different aspects of the geometry. One important line of work, pursued by physicists including Francisco Lobo and Sergei Krasnikov among others, examined whether the bubble walls could be made thinner. The original Alcubierre design had relatively thick walls, and the negative energy requirements scaled with the wall thickness. Thinner walls meant less negative energy. The trade-off was that thinner walls required more careful arrangement of the exotic matter and produced more intense gradients at the boundaries between flat and curved spacetime, which raised concerns about stability. But the basic insight was clear. The wall thickness was a tunable parameter, not a fixed feature of the design, and tuning it appropriately could reduce the energy budget significantly. By the late 2000s, the cumulative effect of all these refinements was that the warp drive energy requirement had been reduced by something like 50 orders of magnitude from the original Alcubierre figure, from Jupiter mass to, in some optimized designs, a few hundred kilograms. The number was still absurd in absolute terms because there was no known source for even a few hundred kilograms of negative energy. But the trajectory of the reductions was suggestive. Each round of refinement found new ways to lower the threshold. There was no obvious reason to think the process had bottomed out. And the question that started to get asked in technical conferences and review papers was whether the threshold might eventually drop to a level where some kind of laboratory-scale experiment became conceivable. That question remained and remains open, but the reduction was real, and it changed how the warp drive question was understood inside the physics community. None of these numbers were practical. Kilograms of negative energy is still kilograms of a substance that, as far as anyone knows, does not exist in the universe in any quantity larger than a few tiny experimental traces. But the direction of the work was clear. Each refinement was pulling the warp drive closer to the boundary between absolutely impossible and merely staggeringly difficult. And while the physicists working on these calculations were generally careful not to overclaim, the implication of their work was unmistakable. Something interesting was happening at the edge of theoretical physics, and it was not slowing down. The next significant step would come from an unexpected direction, and from a country whose contribution to this story is often overlooked: Russia. Specifically, a theoretical physicist named Sergei Krasnikov, who in the mid-1990s had proposed an entirely different approach to the same problem: Russian tubes and a laboratory. Inside NASA, Sergei Krasnikov was a theoretical physicist working at the Pulkovo Observatory in St. Petersburg in the mid-1990s. While the warp drive conversation was just beginning to take shape in the West, Krasnikov was quietly developing a different approach to the same underlying problem. His idea, which he published in a series of papers between 1995 and 1998, did not involve a bubble of manipulated space carrying a spacecraft forward. Instead, it involved building something more like a permanent shortcut. A tube of altered spacetime stretched between two distant points through which a spacecraft could travel at speeds that, from outside the tube, appeared faster than light. The Krasnikov tube, as the construction came to be called, was structurally different from the Alcubierre bubble in an important way. The bubble was a one-time arrangement. You built it, you used it for a journey, and when you arrived at your destination, the bubble dissipated. The tube was a piece of permanent infrastructure. Once constructed, it stayed in place. You could send subsequent ships through it without rebuilding the geometry each time. In principle, an interstellar civilization might construct a network of these tubes between its inhabited systems, the way ancient civilizations built roads between their cities. There was, of course, a problem. Building a Krasnikov tube required exactly the same kind of exotic matter as building an Alcubierre bubble. The amounts involved were, by some estimates, even more extreme, since the tube had to be maintained over a much longer distance. And there was an additional catch. The tube could only be constructed by a spacecraft traveling at sublight speeds from one end to the other. You could not snap a tube into existence between 2 points. You had to build it slowly, from one end the way a tunnel is dug through a mountain, which meant that the first journey along the tube would necessarily take longer than light, and only subsequent trips would be faster. It was, in effect, an infrastructure project of cosmic scale. The Krasnikov work remained relatively obscure outside specialist circles for many years, partly because it appeared in journals that were less prominent than the venues where Alcubierre's paper had been published, partly because the language barrier and the relative isolation of Russian theoretical physics from Western collaboration during the post-Soviet decade reduced its visibility. But within the small community of researchers seriously studying exotic spacetime geometries, the Krasnikov tube was understood as an important variation. It demonstrated, again, that the warp drive idea was not a single isolated solution. It was one member of a larger family of related geometric arrangements, all of which faced the same fundamental challenge of producing exotic matter, but each of which presented different practical trade-offs. Meanwhile, in the United States, a different kind of warp drive research was beginning to take shape. In 2012, a physicist named Harold White, who worked at NASA's Johnson Space Center in Houston, gave a presentation at a conference on advanced propulsion that attracted unusual attention. White was running a small experimental program at a NASA facility, informally known as EagleWorks. The program was looking at, among other things, whether the geometric distortions predicted by Alcubierre's mathematics might be measurable in extremely small-scale laboratory setups. The history of the EagleWorks facility is one of those small institutional stories that say something about how speculative research happens in large organizations. NASA, as a federal agency, is generally cautious about funding work that has no near-term prospect of producing useful results. Most NASA budget goes to projects with clear engineering goals, missions to specific destinations, technology development for established applications. EagleWorks was something different. It was a small lab tucked inside the Johnson Space Center, with modest funding, that was permitted to work on speculative physics questions that the rest of the agency would not have justified on its own. The official name was the Advanced Propulsion Physics Laboratory. The EagleWorks nickname came from the informal culture of the place. It existed because a small number of NASA managers thought that occasional investment in genuinely far-out research might pay off, even if most of it produced nothing. Harold White, who ran the facility, came to it from a background in aerospace engineering. He had worked on conventional propulsion systems before becoming interested in the warp drive question. His research approach was deliberately practical. Rather than trying to build a working warp bubble, which was obviously beyond any plausible budget or technology, he focused on whether the tiny localized space-time distortions predicted by the underlying mathematics might be detectable with sensitive instruments. The reasoning was that if even a small effect could be measured, it would provide experimental confirmation that the mathematics was pointing at something real and would justify further work. If no effect could be measured at the predicted levels, then the entire theoretical framework would be called into question. White's hypothesis was that even if a full-scale warp bubble was impossibly far beyond current technology, it might be possible to detect tiny localized distortions of spacetime using a sensitive instrument called an interferometer. Interferometers measure extremely small differences in the path lengths that two beams of light take. They are used in projects like LIGO to detect gravitational waves from distant black hole mergers. White's idea was that a similar instrument, properly configured, might pick up evidence of intentionally produced spacetime curvature if such a thing could be created in the laboratory. The experimental results from EagleWorks were ambiguous. White and his colleagues reported, at various points, signals that they interpreted as possibly indicating localized spacetime distortion. Other physicists, examining the same data, concluded that the signals could be explained by ordinary instrument effects and atmospheric vibrations. The work was not published in major journals. It did not produce a consensus result. By the late 2010s, the EagleWorks program had been quietly downsized, and White himself had moved to a private research institute called the Limitless Space Institute, focused on interstellar propulsion. The institutional memory of the EagleWorks era now lives mostly in the small community of researchers who continue to work on related questions. It would be easy to dismiss the EagleWorks story as a footnote, a small piece of speculative work that did not produce a definitive result and is now mostly remembered as a curiosity. But the historical importance is real, and it is worth being precise about it. For the first time, a major space agency had funded, at least at a modest level, a laboratory program aimed at exploring the warp drive idea. The work was not crackpot. It was not the product of a single eccentric individual. It was a small but legitimate piece of research carried out within an established institution. And while it did not produce a breakthrough, it changed the social position of the warp drive question. The idea was no longer purely theoretical. It had become, at least briefly, an experimental subject. This shift mattered for the next stage of the story, because in the years that followed the EagleWorks work, several other research programs around the world began taking the warp drive question more seriously. New theoretical refinements continued to appear. The numbers continued to come down. And then, in 2021, a young German physicist named Erik Lentz published a paper that did something nobody had quite managed before. He proposed a warp drive that did not require negative energy at all. The quiet paper that almost nobody knew what to do with. Erik Lentz was a postdoctoral researcher at the University of Göttingen in Germany in 2021. He had been working on questions involving gravitational physics for several years, and he had become interested in the warp drive problem, partly out of frustration with the standard assumption that exotic matter was unavoidable. The standard assumption, in his view, deserved a more careful look. The argument that warp drives required negative energy density rested on a set of mathematical conditions called the energy conditions, which were normally treated as fundamental constraints in general relativity. Lentz wondered whether those conditions had been applied too strictly to the warp drive problem. In March of 2021, he published a paper in Classical and Quantum Gravity, the same journal that had carried Alcubierre's original work 27 years earlier. The paper had a deliberately unassuming title. It was called Breaking the Warp Barrier, Hyperfast Solitons in Einstein-Maxwell Plasma Theory. The technical jargon in the title was doing serious work. A soliton, in physics, is a self-contained wave packet that maintains its shape as it propagates. The phrase Einstein-Maxwell plasma referred to a specific framework for describing how matter and electromagnetic fields interact within general relativity. The paper claimed, in essence, that within this framework, a warp drive solution could be constructed using only positive energy sources, ordinary matter, the kind of stuff the universe is full of. Erik Lentz's paper deserves a closer look because it represents the most genuinely surprising development in warp drive research in the last decade, and the response to it inside the physics community has been complicated in ways that are worth understanding. Within weeks of the publication, it was being discussed in physics blogs, in popular science articles, and in the small community of professional researchers who follow this area closely. The headline result, that a warp drive could be constructed without negative energy, was striking enough that it attracted both serious attention and serious scrutiny. The technical heart of Lentz's paper involves what he calls solitons, which are stable wave packets that maintain their shape as they propagate. Solitons are well-established objects in many areas of physics, from fluid dynamics to optics to plasma physics. They appear naturally in systems where certain nonlinear effects balance against each other to produce stable structures. Lentz's claim was that the equations governing the interaction of matter and electromagnetic fields in curved space-time, called the Einstein-Maxwell equations, admit Soliton solutions that have the geometric properties of a warp bubble, and that these solitons can be constructed using positive energy sources. The technical details of how this was achieved involve specific manipulations of the plasma physics and the space-time geometry that other researchers have been working through carefully. If this claim was correct, it represented a genuinely surprising breakthrough. For nearly 3 decades, every serious warp drive proposal had relied on negative energy in some form. The negative energy requirement had been treated as a fundamental obstacle, the reason the whole idea remained safely in the territory of mathematical curiosity rather than practical engineering. Lentz's paper suggested that this obstacle might be a mistake, not because the physics had changed, but because the geometry could be configured differently. The response from the rest of the physics community was, as you might expect, complicated. Some researchers were cautiously enthusiastic. The mathematics in Lentz's paper appeared, on initial inspection, to be valid. The construction was novel. The implications, if they held up, were significant. Other researchers were skeptical. They argued that Lentz's solution had hidden problems, that what looked like positive energy in his framework would turn out, on closer analysis, to require negative components after all. The debate was not loud. It happened mostly in journal papers and in technical conferences. But it was real, and it has continued for several years now, with the question of whether Lentz's positive energy solitons actually deliver on their promise remaining genuinely unresolved. Several follow-up papers have appeared since 2021. Some support the basic result, arguing that the negative energy concerns are based on misreadings of the mathematics. Others have argued that Lentz's construction, on closer examination, contains hidden negative energy components that he did not fully account for. Still others have argued that the soliton stability is not as robust as the original analysis suggested, and that perturbations would cause the structure to collapse. The debate is genuinely unresolved as of the most recent serious reviews. What we can say is that the paper opened a question that had been considered closed for nearly 3 decades, and that the question is now being actively investigated rather than dismissed. That, in itself, is a significant change in the state of the field. Now, you might reasonably ask why a result this important has not received more public attention. The answer is that the result is not yet settled. Physics papers, even very interesting ones, do not become accepted physics until they have been examined, replicated, and either confirmed or refuted by independent work. Lentz's paper is still in the early phases of that process. The state of the field, as of the most recent honest assessments, is that the positive energy warp drive remains an open question, possibly real, possibly an artifact of the specific mathematical framework Lentz used. Time will tell, in the relatively slow way that fundamental physics questions usually resolve themselves. But the historical importance of the Lentz paper does not depend on whether his specific construction ultimately survives. The importance is that the question, for the first time, has been opened. Whether warp drives require exotic matter is no longer treated as an obvious yes. It is now treated as a research question, one that serious physicists are working on actively, and one that the answers may not be as simple as the standard textbook treatment suggests. If the positive energy approach turns out to be valid, the consequences are difficult to overstate. The warp drive would no longer require building a substance that does not exist. It would require building something out of ordinary matter, in vastly larger quantities than current technology allows, but at least within the category of substances that the universe actually contains. The wall would still be there, but the path around the wall would no longer be made of impossible ingredients. It would be made of merely staggeringly difficult ones. And the difference between impossible and staggeringly difficult is, in the long arc of history, the entire space within which human technological progress has happened. Flying was impossible until it was merely difficult. Reaching the moon was impossible until it was merely difficult. The structure of major technological revolutions has consistently been a slow walk from clearly impossible to obviously achievable, mediated by decades or sometimes centuries of careful theoretical and experimental work. The warp drive, if Lentz is correct, may have just taken its first significant step along that walk. We will not know for some time. But the conversation has shifted. And once a conversation in physics shifts, the field rarely goes back to where it started. A note before we continue. Before we move into the deeper problems that come attached to the warp drive idea, the causality issues and the wormhole alternatives, and the strange place where negative energy actually does exist in laboratories, a quick word. If this investigation is landing with you tonight, if the slow, careful work that physicists are doing on these questions is something you find genuinely interesting, consider subscribing to Astral Lab. This is what this channel does. Long, careful walks through the open questions in modern physics. There is more of it coming. For now, we continue. The problem that has no engineering fix. Now we have to talk about the strangest part of the entire story. Because even if the negative energy problem was somehow solved, even if Lentz's positive energy solitons turned out to be correct, even if every engineering obstacle were overcome and humanity built a functioning warp drive tomorrow, there would still be a deeper problem waiting at the other end, a problem that cannot be engineered around, a problem that emerges from the structure of physics itself, and that physicists have been wrestling with quietly for decades. Faster than light travel in any form appears to be equivalent to travel backward in time. This is one of those statements that sounds at first like an exaggeration or a piece of dramatic physics rhetoric. It is not. It is a direct consequence of the geometry of space-time that Einstein worked out a century ago. The argument is technical, but the essential idea can be sketched without too much trouble. In special relativity, the order in which two distant events appear to occur depends on the motion of the observer measuring them. Two events that look simultaneous from one reference frame can look successive from another. This is called the relativity of simultaneity, and it is a well-established and experimentally confirmed feature of the universe. Now here is the consequence. If you have a signal that travels faster than light, you can use it to send information between two events in a way that, from some reference frames, makes the signal arrive before it was sent. The mathematics is unambiguous. Faster than light signals, combined with the relativity of simultaneity, allow loops where the effect precedes the cause. And once you have that, you have time travel into the past, with all of its accompanying paradoxes. The most famous of these paradoxes is the grandfather paradox. The idea is straightforward. If you can travel into the past, you could in principle do something that prevents your own birth, which would mean you never traveled in the first place, which means the prevention never happened. And so on, into an unresolvable contradiction. The grandfather paradox is sometimes treated as a piece of philosophical entertainment, but in physics it is a serious problem. Theories that allow it tend to break in subtle ways. Probability stocks summing to 1. Causality becomes ambiguous. The internal consistency of the equations begins to fray. Stephen Hawking, the British theoretical physicist who spent much of his career thinking about the relationship between gravity and quantum mechanics, was sufficiently concerned about this that he proposed something called the chronology protection conjecture. The conjecture, which Hawking sketched in a 1992 paper, claims that the laws of physics conspire to prevent the formation of closed time-like curves. Whenever an arrangement of matter and energy starts to look like it might create a path through time, some physical effect intervenes to disrupt it. Hawking did not have a complete proof of the conjecture. He suggested it as a working hypothesis. But the conjecture was motivated by his strong intuition that a universe permitting time travel into the past would not be self-consistent. The chronology protection conjecture deserves a slightly closer look because it represents one of the most interesting points where speculative physics meets fundamental questions about the structure of physical law. The paper Hawking published in 1992 was titled, simply, Chronology Protection Conjecture, The paper was relatively short, and the argument was structured around a specific observation. Whenever the equations of general relativity allowed for the formation of closed, time-like curves, paths through space-time that loop back on themselves and would permit travel into the past. Hawking found that quantum effects in the regions where the curves were about to form produced infinite or very large stresses on the geometry. These stresses, in his analysis, would prevent the curves from actually forming. The universe, in effect, would self-destruct any region where a time machine was about to appear. The conjecture is not a theorem. Hawking did not prove that chronology protection must hold in all cases. He provided what he called strong evidence that something like it appeared to be true in the specific cases he had examined, and he suggested that the principle might be general. Other physicists working on similar questions have produced mixed results. Some calculations support the conjecture. Some calculations seem to contradict it. The general consensus, if there is one, is that the question is genuinely open. We do not yet have a complete theory of quantum gravity, and until we do, definitive statements about whether the universe permits time travel are not really possible. This matters for the warp drive question in a specific way. The Alcubierre bubble, the Krasnikov tube, and the Lentz soliton all permit, in principle, the construction of closed, time-like curves through appropriate arrangements of the geometry. The same loophole that allows faster-than-light travel also allows backward time travel, because the two are mathematically the same operation. If you can do one, you can do the other. And if the chronology protection conjecture is correct, then something must prevent the warp drive from actually functioning. Some physical effect that we have not yet identified must intervene whenever the geometry starts to bend toward a configuration that would allow paradoxes. Several physicists have proposed candidates for what this protection mechanism might be. Hawking himself suggested that quantum effects near the boundaries of the warp bubble might cause it to collapse, producing a kind of feedback loop where the bubble destroys itself as soon as it tries to form. Other researchers have proposed that the energy required to maintain the bubble against its own quantum fluctuations might diverge to infinity as the bubble approaches a configuration that allows paradoxes. The technical details are debated, but the basic concern is shared. The mathematics that allows faster-than-light travel also allows time travel, and the universe may simply not permit the latter. There is also a more philosophical angle to the causality question that is worth mentioning briefly. Some physicists, faced with the conclusion that the warp drive permits time travel and that time travel permits paradoxes, have proposed alternative resolutions that do not require the chronology protection conjecture. One approach, associated with the physicist David Deutsch, suggests that paradoxes could be resolved through quantum mechanics, with multiple branches of the wave function containing the different outcomes of paradoxical actions. Another approach, associated with Igor Novikov, proposes that the laws of physics simply enforce self-consistency, so that any action you take in the past must already be part of the history that led to your present. These are speculative ideas, but they illustrate that the chronology problem is not necessarily a deal-breaker. There may be ways for the universe to permit faster-than-light travel while still avoiding paradoxes. It is also worth pausing on what this means for the question of whether the warp drive will ever actually work. There are essentially two possibilities. Either the chronology protection conjecture is correct, in which case the warp drive faces an obstacle that no amount of engineering can overcome, because the protection emerges from the laws of physics themselves. Or the conjecture is wrong, in which case the warp drive is, in principle, possible, but its existence implies a universe where backward time travel and its associated paradoxes are also possible. Neither of these outcomes is comfortable. The first means we're stuck. The second means we have not properly understood causality. Physicists have not yet reached a consensus on which possibility is correct. And there are smaller, more technical problems that come along with the warp drive, even if the chronology issues turn out to be solvable. Inside the bubble, the spacecraft is in a region of completely flat space-time, disconnected from anything outside. This creates what physicists call a horizon problem. Information cannot pass from the interior of the bubble to its exterior, or vice versa, while the bubble is moving faster than light. This means that the crew of a warp ship would have no way to communicate with their destination, would have no way to adjust course in flight, and would arrive at their destination with no way to know what had been happening there during the trip. There are also concerns about Hawking radiation forming at the bubble walls, similar to the radiation that emerges from black hole event horizons, which might destroy the bubble from the inside out. None of these problems are necessarily fatal. Solutions had been proposed for some of them. But the cumulative picture is that the warp drive, even in its most optimistic versions, comes attached to a long list of physical complications that have nothing to do with engineering, and that may have no engineering solutions. The wall is there. The path around the wall is real. But the path is not empty. It has obstacles built into it by the structure of physics itself, and those obstacles do not yield to better materials or larger budgets. The other door, and why it is worse. If warp drives are the most famous proposed approach to faster-than-light travel, wormholes are the second most famous. They have appeared in popular culture for decades, in films and novels and television episodes, usually depicted as glowing tunnels through which ships pass from one part of the universe to another in a matter of seconds. The popular depictions are not entirely fictional. Wormholes are real solutions to Einstein's equations. They have been studied seriously by theoretical physicists for almost a century. And they offer, in principle, an entirely different route around the wall than the warp drive does. They also, unfortunately, come with their own set of fatal complications. The history of wormhole research goes back even further than most people realize, though most of the early work treated wormholes as mathematical curiosities rather than serious propulsion proposals. The first solutions describing tunnels through space-time were found by Ludwig Flamm in 1916, almost immediately after Einstein published the general theory of relativity. Flamm noticed that the equations describing a black hole appeared to permit a kind of bridge connecting the black hole to another region of space-time. The interpretation of this bridge was unclear at the time, and it would be decades before the geometry was fully understood. Albert Einstein himself, working with Nathan Rosen in 1935, produced a more developed version of the same idea, which became known as the Einstein-Rosen bridge. The bridge, in their analysis, was unstable. Anything trying to pass through it would be crushed by the geometry as it formed and dissipated. The first serious modern paper on wormholes as practical shortcuts appeared in 1988 in the American Journal of Physics. The authors were Michael Morris and Kip Thorne, working at the California Institute of Technology. The paper had an unusual origin story. Kip Thorne had been consulting on the novel Contact by Carl Sagan, who wanted to include a method of interstellar travel that did not violate known physics. Sagan asked Thorne for advice. Thorne, who had been working on general relativity for decades, became interested enough in the question to investigate it seriously. He and Morris worked out the conditions under which a wormhole could function as a traversable shortcut, rather than as the kind of unstable singularity that physicists had previously considered. What Morris and Thorne did was different from earlier wormhole work. They asked, specifically, what kind of matter and energy distribution would be required to produce a wormhole that was stable and traversable, meaning that an object could pass through it without being destroyed. The answer, which they derived carefully, was that you needed a matter distribution with negative energy density in the throat of the wormhole. The negative energy would push outward against the natural tendency of the geometry to collapse, holding the tunnel open against its own gravitational attraction. The amount of negative energy required scaled with the size of the wormhole, and for any wormhole large enough to be useful, the amount became enormous. A wormhole, in the Morris-Thorne picture, is a tunnel through space-time that connects two regions of the universe through a path much shorter than the ordinary distance between them. The geometry is sometimes described using a two-dimensional analogy. Imagine the universe as a flat sheet of paper. 2 points on the paper are separated by a long distance if you measure across the surface. But if you fold the paper so that the 2 points come close together, you can drill a hole through both layers and connect them directly. The straight line through the hole is much shorter than the path across the paper. A wormhole does the same thing in 3 dimensions, except that the folding happens in higher dimensional space-time that is difficult to visualize directly. If wormholes existed and could be stabilized, they would provide an extraordinary shortcut. A ship entering one end would emerge from the other end almost immediately, regardless of how far apart the two ends were in ordinary space. Light years would become a few moments of travel. The wall would be sidestepped entirely, because the ship would never actually be moving faster than light through any local patch of space. The two endpoints would simply be brought close together by the folding of space-time. The trouble is that wormholes, even more than warp drives, require negative energy to function. Without some kind of exotic matter holding the throat of the wormhole open, the geometry collapses immediately. Any ordinary matter trying to traverse the wormhole would cause the walls to close around it, pinching the tunnel shut before the matter could get through. The negative energy is needed not just to build the wormhole, but to keep it stable against its own tendency to collapse. And the amount required, in most calculations, is comparable to or larger than the amounts required for warp drives. There is one piece of wormhole physics that is worth understanding for its sheer strangeness, and that is the time machine aspect. If you take a stable wormhole and accelerate one of its mouths to high speed and then bring it back, the relativistic time dilation that affects the moving mouth means that when the two mouths are brought close together again, they are not synchronized. A clock at the stationary mouth shows a later time than a clock at the moving mouth by an amount that depends on the speed and duration of the journey. If you then look through the wormhole, you are not looking at the present at the other end. You are looking at the past. Anything entering the moving mouth emerges from the stationary mouth at a time earlier than it entered. The wormhole becomes a time machine. This is not a hypothetical addition to the wormhole picture. It is built into the geometry. Any traversable wormhole, given enough manipulation of its endpoints, automatically becomes a path to the past, which connects the wormhole problem directly to all the causality issues we just walked through. And the practical problems with wormholes are arguably worse than those for warp drives. A warp drive only needs to exist for the duration of a single trip. A wormhole, to be useful, has to be maintained indefinitely. The exotic matter requirement is therefore not a one-time investment, but an ongoing infrastructure cost. And the technology for actually constructing a wormhole, even granting that you had the exotic matter available, is essentially unknown. The mathematics describes what a stable wormhole would look like if it existed. It does not describe any process by which such a thing could be built starting from the ordinary universe we live in. There is one possible exception to this. Some physicists have speculated that microscopic wormholes might exist naturally in the structure of space-time at extremely small scales, on the order of the Planck length, which is roughly 10 to the negative 35 meters. At these scales, the quantum nature of space-time becomes important, and the geometry might be filled with a constantly fluctuating foam of tiny wormholes appearing and disappearing too quickly to detect. If such microscopic wormholes existed, one could, in principle, imagine a technology that somehow stabilized and enlarged one of them into a usable size. This is, however, far beyond anything resembling current understanding. It is closer to a hope than to a research program. The wormhole approach to faster-than-light travel, then, sits in a strange position. It is mathematically well defined. It is genuinely older as a research subject than the warp drive. It would, if it worked, provide an even more dramatic shortcut, but it requires exactly the same physically unavailable ingredients as the warp drive, plus additional requirements of its own, plus the same causality problems, plus a complete absence of any plausible construction method. For all these reasons, wormhole research has remained largely theoretical, with little of the active investigation that warp drives have attracted in the last decade. It is a beautiful idea that has not been improved upon in the way that the warp drive has been. The door is still there, but nobody has found a way to open it. Where negative energy actually lives. In the real world. Throughout this entire investigation, we have kept referring to negative energy as if it were a purely theoretical substance, the kind of thing that exists only in mathematical models. That is not quite accurate. Negative energy does exist in the real universe. It has been measured in laboratories. The amounts involved are extraordinarily small, and the configurations in which it appears are extremely specific, but the existence is genuine. And the story of how this was discovered, and what its limits are, is one of the more remarkable side branches of 20th century physics. The discovery is associated with a Dutch physicist named Hendrik Casimir, who in 1948 was working at the Philips Research Laboratories in the Netherlands. Casimir was studying the forces that arise between small particles suspended in colloidal solutions. The standard explanation for these forces involved fluctuating electric dipoles, which interact with each other through quantum mechanical effects. As Casimir worked through the calculations, he realized that a similar effect should apply not just to particles, but to ordinary surfaces placed close together in a vacuum. If you took two flat metal plates and brought them very close together, the quantum vacuum between them should exert a small but measurable force pulling them together. The reasoning behind this prediction is one of the strangest pieces of physics in the last 100 years, and it is worth pausing on. According to quantum theory, empty space is not actually empty. Even in the most perfect vacuum, with all matter and radiation removed, the quantum fields that pervade the universe are constantly fluctuating. Virtual particles appear and disappear continuously, too quickly to be detected directly, but with measurable effects on the surrounding environment. The vacuum has a baseline energy, sometimes called the zero-point energy, which arises from these fluctuations. Now, here is where Casimir's insight came in. The fluctuations in the vacuum involve waves of various wavelengths. When you bring two flat surfaces close together, only certain wavelengths can fit between them. The longer wavelengths are excluded. Outside the surfaces, all wavelengths are present. The result is that the energy density of the vacuum between the plates is slightly lower than the energy density outside the plates. The difference is tiny, but it produces a real force, pushing the plates toward each other. And crucially, the region of vacuum between two Casimir plates contains a small amount of genuinely negative energy density. Not negative in some abstract mathematical sense. Negative in the same way that ordinary matter contains positive energy density. The first experimental measurements of the Casimir force were performed by Marcus Sparnai in 1958, but the precision was not high enough to be conclusive. The definitive measurements were made in the late 1990s by Steve Lamoureux at the University of Washington and by Umar Mohadeen at the University of California, Riverside, using extremely sensitive torsion balancers and atomic force microscopes. The measurements confirmed the predictions of Casimir's 1948 calculation to within a few percent. The effect is real. The amount of negative energy in the gap between two plates separated by a few hundred nanometers is extremely small, on the order of microjoules per cubic centimeter. But it is genuinely negative. The Casimir effect is the only confirmed example of a violation of the classical energy conditions that show up everywhere else in physics. This is the only well-established source of negative energy in the known universe. It is genuinely there. It can be measured. And, in principle, it could be used as a source for the kind of exotic matter that warp drives and wormholes require. The problem is that the amounts involved are absurdly small. The negative energy density between two Casimir plates at typical laboratory separations is many orders of magnitude smaller than what would be needed to power even the most optimistic warp drive design. To accumulate enough negative energy for a useful spacecraft, you would need a structure containing impossibly many Casimir plates, packed into impossibly small volumes, in arrangements that would be extraordinarily difficult to maintain. Some physicists have explored whether more exotic configurations might produce larger negative energy densities. There is work on what are called squeezed vacuum states, where the quantum properties of light can be manipulated to produce regions where the energy density falls below the standard vacuum baseline. There is work on certain configurations of quantum fields in curved spacetime where negative energy densities can in principle be larger. There are theoretical proposals involving exotic materials that might amplify the Casimir effect. None of these approaches has yet produced negative energy in quantities even remotely close to what a warp drive would require. But they exist as research directions, and the amount of negative energy you can in principle obtain is not zero. The honest assessment, as of the most recent serious reviews, is that negative energy is real, that it can be created in extremely small quantities in laboratory settings, and that scaling it up to anything useful for propulsion appears to require breakthroughs that nobody currently knows how to achieve. The Casimir effect tells us that the universe permits negative energy. It does not yet tell us how to make enough of it to matter, but the door has been opened a crack. Whether it can be opened wider is one of the open questions in modern theoretical physics. And here is the subtle but important point. Before Casimir's discovery in 1948, negative energy was considered impossible in the same sense that motion faster than light was considered impossible. After Casimir, it became a real but very tiny phenomenon. The category of impossible was reduced to the category of difficult. We do not know whether the same shift will happen with the quantities required for warp drives. We do know that the universe is more permissive about negative energy than 19th century physics would have suggested. And we know that the research is ongoing, slowly, in laboratories around the world, where physicists with extremely sensitive instruments continue to push at the boundaries of what the quantum vacuum will allow. What an alien civilization's drive would look like from Earth. There is one final thread to follow before we close, and it is one that connects the abstract physics of warp drives to a question that has captivated humanity for as long as we have looked at the night sky. If faster than light travel is possible, and if any civilization in the galaxy has ever figured out how to do it, then their spacecraft should be detectable in some way. Their warp drives, if they exist, should leave signatures. And in the last decade, a small but serious community of physicists and astronomers has started asking what those signatures might look like and whether any of them have ever been seen. The starting point for this research is the recognition that a working warp drive of the kind Alcubierre or Lentz described would necessarily produce certain unavoidable physical effects in the surrounding universe. The contraction of space in front of the bubble and the expansion behind it would generate gravitational waves. The acceleration of the bubble itself, even though it does not involve local acceleration of any matter, would produce ripples in the space-time geometry that propagate outward at the speed of light. These ripples would, in principle, be detectable by sensitive gravitational wave observatories of the kind that have been operating on Earth for the last decade and a half. The first paper to take this question seriously appeared in 2021. The author was Sebastian Schuster, working at the University of Vienna, and the paper examined what kind of gravitational wave signatures a hypothetical warp drive would produce. The conclusions were striking. A warp drive carrying a spacecraft of even modest size, at a sensible fraction of light speed, would generate gravitational wave signals that would be visible across the galaxy. Not faint signals at the limit of detection. Distinctive, loud signals that no natural process could produce. If anyone in the Milky Way had ever built a warp drive and used it, current gravitational wave detectors should have seen the signature, and we should be looking for it actively. This connects the warp drive question to a broader research area called technosignature science. Technosignatures are observable signatures of technological civilizations, as distinct from biosignatures, which are signatures of biological life. The search for biosignatures looks for things like oxygen in the atmospheres of distant planets, or particular ratios of molecules that might indicate biological metabolism. The search for technosignatures looks for things that only intelligence could produce. Radio signals with artificial structure. Patterns of light emission that suggest engineered megastructures. And now, increasingly, gravitational signatures that suggest engineered manipulation of space-time. The astronomer Paul Davies, working at Arizona State University, and the astronomer Milan Sirkovic, working in Belgrade, have been among the most active writers on the techno-signature framework. Their argument is that if intelligent civilizations exist elsewhere in the universe, and if any of them have developed advanced technology, then they should be leaving observable traces. The fact that we have not yet detected any such traces is itself a piece of evidence. It tells us that either intelligent civilizations are rare, or that they do not develop the kinds of technologies we would expect, or that the technologies they develop look different from our assumptions. Each of these possibilities has implications for how we think about our own place in the cosmos. The techno-signature framework for the warp drive question is worth exploring a little further because it represents one of the more recent developments in how physicists think about the possibility of advanced civilizations. The basic argument runs as follows. If intelligent life is reasonably common in the universe, and if at least some intelligent civilizations develop advanced technology, then the universe should contain detectable evidence of that technology. The evidence might take many forms: radio signals leaking from communication systems, heat radiation from large-scale engineering projects, optical signatures of laser propulsion or interstellar communication beacons, gravitational signatures of large-scale manipulation of space-time. Each of these is a potential techno-signature, and each has its own search strategy. Warp drives fit into this framework in an interesting way. They are exactly the kind of technology that should be detectable across vast distances, because their fundamental operation produces signals that propagate outward through the universe. If even one civilization in the Milky Way had been using warp drives for 100,000 years, the gravitational wave background of our galaxy would, by the predictions of Schuster and others, look dramatically different from what we observe. The fact that it does not look different is, on this argument, weak evidence that nobody has been using warp drives. Either nobody has them, or the technology turns out, on closer examination, not to work after all, or it produces signatures we do not yet know how to recognize. There is one more piece of context worth adding here, which is that the absence of evidence for warp drive technology fits into a larger pattern that physicists sometimes call the Fermi paradox. The paradox, named after the physicist Enrico Fermi, is the question of why we do not see clear evidence of intelligent civilizations elsewhere in the galaxy. Given that the basic conditions for life appear to be common, and the galaxy is much older than the time it would take for an intelligent civilization to spread across it. Various resolutions to the paradox have been proposed. Maybe intelligent life is rare. Maybe civilizations destroy themselves before they spread. Maybe the limits of physics prevent spreading at all. The warp drive question is directly relevant to this last possibility. If the chronology protection conjecture turns out to be correct, and warp drives are not actually possible, then the speed of light limit may be a genuine and permanent barrier to interstellar civilization, which would itself be a partial answer to the Fermi paradox. The universe might simply be too large to colonize, even for civilizations far more advanced than our own. This is not proof of anything definite. The arguments rest on assumptions about how widespread intelligent life is, how long civilizations last, and what kinds of technology they develop. All of these assumptions are themselves debated, but the framework suggests something that is worth taking seriously. The warp drive is not just a question about whether humanity can build one. It is also a question about whether anyone else in the galaxy has built one. And the answer so far appears to be that they have not. Which leaves us, at the end of this investigation, with one final consideration. The total energy budget required to actually use a warp drive at interstellar distances, in any of its proposed forms, is staggering even by cosmic standards. Some estimates suggest that powering a single round trip to Proxima Centauri using even an optimized warp drive would require the energy output of a substantial fraction of a star. That is the amount of energy that nature took billions of years to produce in the first place. The wall has been walked around mathematically. Walking around it physically remains a project for a civilization we have not yet become. Before we move into the final assessment, there is one more piece of context worth holding. The history of warp drive research, taken as a whole, is genuinely unusual within physics. It is one of the very few research areas where the boundary between speculative theory and serious investigation has been actively contested for 3 decades. Most exotic ideas in physics either get absorbed into the mainstream relatively quickly, the way Einstein's relativity did within a couple of decades of its publication, or they get filed away as mathematical curiosities and forgotten. The warp drive has done neither. It has occupied a strange middle ground, taken seriously enough that established physicists publish papers on it in respected journals, but considered too speculative for major institutional funding or coordinated experimental programs. This middle ground is rare. It is the kind of position that ideas occupy when the data is not yet decisive in either direction, and when the underlying questions are interesting enough to keep researchers engaged regardless of the practical prospects. It is also worth noting how international this research program has been. The original Alcubierre paper came from Mexico through Cambridge. The Van den Broek refinements came from the Netherlands. The Krasnikov tubes came from Russia. The EagleWorks program came from the United States. The Lentz paper came from Germany. The Schuster gravitational wave analysis came from Austria. The Crane-Korteweg style, zone of avoidance work, that informs our understanding of large-scale structure came from South Africa. The Casimir effect was first proposed in the Netherlands and definitively measured in the United States. The chronology protection conjecture came from Britain. The wormhole work came from California with input from Carl Sagan in New York. The picture that emerges is of a globally distributed research community, working in many countries and many languages, contributing pieces to a puzzle that no single national program could have assembled on its own. The warp drive question has been, in a quiet way, one of the more genuinely international research projects of the last 3 decades. There is also a sociological observation worth making about the warp drive research community itself. The physicists who work on these questions tend to be careful, technically rigorous, and openly aware of the long odds against any practical outcome. They are not, on the whole, the kind of researchers who promise breakthroughs at press conferences. They publish in peer-reviewed journals. They attend small specialized conferences. They engage in slow technical disagreements with each other through the formal apparatus of academic publication. When popular accounts of warp drive research overstate the prospects, the working physicists usually push back, quietly but firmly, in subsequent papers and interviews. The community has a sense of its own credibility and protects it carefully. This is part of why the warp drive question has retained its scientific seriousness over 3 decades, despite the inevitable temptation to treat it as a piece of science fiction wishful thinking. The people doing the work have, on the whole, refused to let it become that. And there is one final piece of context that is worth setting before we close. The warp drive question, in its modern form, sits at the intersection of several different research areas. General relativity provides the geometric framework. Quantum field theory provides the constraints on what kinds of matter and energy can exist. Plasma physics provides the tools for analyzing how electromagnetic fields interact with the structure of spacetime. Cosmology provides the observational context for thinking about the large-scale behavior of the universe. None of these fields, on its own, would be sufficient to make progress on the warp drive question. The question requires a combination of expertise that is genuinely difficult to assemble in a single research group. This is part of why the progress, when it comes, tends to come in small increments rather than dramatic breakthroughs. The boundaries between subfields are real, and crossing them productively takes time and patience. The warp drive question has been, in this sense, a test of how well 21st century physics can integrate its various specializations into a coherent investigation of a single difficult problem. And there is one more consideration that is worth holding alongside the technical work. The warp drive question is, in some ways, a test of human imagination as much as a test of physical law. The mathematics that Alcubierre wrote down in 1994 could have been written down at any point in the previous 8 decades. The equations of general relativity were available. The geometric framework was in place. The tools existed. What was missing for those 80 years was someone willing to ask the question in exactly the right way and someone willing to take the answer seriously when it arrived. The history of the warp drive is, in this sense, a history of a question that had been hiding in plain sight, waiting for someone to notice it. And when it finally was noticed, the work that followed has been a slow, careful exploration of what the universe might be willing to let us do. If we asked it nicely enough, and built our instruments carefully enough to find out. There is one more observation that fits here, because it speaks to something deeper about how physics actually progresses. The progress on the warp drive question, such as it has been, has not come from anyone trying to build a warp drive. It has come from physicists working on adjacent problems, on related geometries, on the structure of negative energy, on the foundations of general relativity, on the limits of what energy conditions actually require. Each of these adjacent threads has contributed something that, taken together, has gradually changed how the warp drive question is understood. This is the way most progress in fundamental physics actually happens. Not through targeted assaults on famous problems, but through accumulated insights from related work, each of which seems minor in isolation, but adds up over decades to a substantially different understanding of the original question. The warp drive may or may not eventually become physically possible. But the work that has been done in trying to understand whether it could be possible has already changed our picture of what space-time actually permits, and that change is real regardless of the engineering outcome. Mission brief, and what this all adds up to. We have walked a long way through this investigation, from the 4 light-year distance to Proxima Centauri, through the rocket equation that makes ordinary engineering hopeless, through Einstein's wall and the loophole hidden inside the expansion of space, through the 1994 paper that opened the modern warp drive conversation, through 3 decades of refinements that have slowly reduced the impossible to the merely staggeringly difficult, through the causality problems that may make the whole enterprise self-defeating, through wormholes and the Casimir effect, and the search for alien warp signatures across the gravitational wave background of our galaxy. So the question we started with, the question in the title of this script, deserves a careful answer. Have scientists found a real way to travel faster than light? The honest reply is that they have found a real path on paper, not in steel, not in working spacecraft, not even in laboratory prototypes large enough to send across a room, let alone across a galaxy. But the path on paper is genuine. It is not a fantasy. It is a piece of mathematics that emerges directly from the same equations Einstein wrote down a century ago, and it has been refined and extended by serious physicists working in serious institutions for 30 years. The question is no longer whether the universe forbids the idea. The question is whether the universe forbids the practical construction, and that, as of the most recent honest assessments, is genuinely unresolved. The wall is still there. The speed of light remains, locally, the fastest anything can move through any patch of space. Einstein's geometry has not been overturned. What has changed is the conversation around the wall. We now know that the geometry of general relativity allows for arrangements where space itself does the moving, while the spacecraft inside sits motionless. We know that the negative energy required to produce these arrangements, while still enormous, is not necessarily at the planet mass scale. We know that there are proposals, like the one Erik Lentz published in 2021, that may not require negative energy at all, though the verdict on those proposals is still pending. And we know that the universe, somewhere in the strange quiet corners of its quantum vacuum, does permit small amounts of negative energy to exist. The door is not closed. It is not exactly open either. But it is no longer locked in the way that physicists once assumed it was. What this means for human civilization, in any practical sense, is that interstellar travel remains as far away tonight as it was 100 years ago, No warp drive is going to launch in our lifetimes. No spacecraft is going to reach Proxima Centauri in a year. The path forward, if there is one, requires breakthroughs that we cannot currently foresee. The work continues. Papers are still being written. Experiments are still being designed. The conversation, in academic journals and at small conferences and in late-night discussions among physicists who have spent their careers thinking about these problems, is still happening. It is slow, careful work. It does not produce headlines very often, and it does not promise any particular outcome. But the work matters, even if the warp drive never actually gets built. Because the questions it raises about the nature of space-time, about the limits of what is physically possible, about whether the universe permits the kinds of geometric manipulations that classical relativity allows on paper, are some of the most fundamental questions in modern physics. The warp drive may turn out to be permanently impossible. The chronology, protection conjecture may turn out to be correct. The negative energy requirements may turn out to be insurmountable. Even so, the research itself has deepened our understanding of how the universe is put together, and that understanding, regardless of whether it ever produces a starship, is its own kind of progress. There is something worth saying about why this question matters, even if the engineering never works out. The warp drive is, in many ways, a test case for a deeper question about the nature of physical law. The question is whether the laws of physics, as we currently understand them, leave enough room for advanced civilizations to do dramatic things, or whether the laws are restrictive enough that the universe is essentially closed to anything resembling galactic-scale travel or communication. The warp drive sits at the boundary between these two possibilities. If it works, the laws of physics are more permissive than they appear at first glance, and the future of any intelligent civilization in the universe contains possibilities we have only begun to imagine. If it does not work, the laws of physics are stricter than we thought, and the future of intelligent civilizations is bounded in ways that have important implications for how we think about our own long-term prospects. Either answer matters. And it is worth ending on a slightly broader observation. The history of physics, taken as a whole, is a history of expanding the category of what is considered possible. Things that were considered impossible by one generation have routinely turned out to be merely difficult for the next, and the boundary between impossible and difficult has consistently moved in the direction of allowing more, not less. Flight was impossible. Manned spaceflight was impossible. Computing at the scales we now take for granted was impossible. Each of these was, at one point, the kind of thing serious people dismissed as science fiction. Each of them is now ordinary engineering. The warp drive may turn out to be a genuine exception to this pattern, a piece of physics that really is permanently impossible because the universe really does forbid it. Or it may turn out to be one more example of the pattern, an impossible thing that gradually becomes difficult and eventually becomes ordinary. We do not know yet. The work is ongoing. The conversation continues. Somewhere out there tonight, in laboratories and offices around the world, physicists are working on the next paper in this long conversation. The conversation that began with Einstein in 1905, that took an unexpected turn with Alcubierre in 1994, and that has continued slowly and quietly. Through the work of Van den Broek and Krasnikov, and White and Lentz, and others whose names most of us will never know. The wall is still there. The path around it remains genuinely uncertain, but the question of whether scientists have found a real way to travel faster than light has, at the very least, become a serious question instead of a closed one. And that, in physics, is often how the most interesting stories begin. The stars are still very far away, but they are no longer entirely out of reach in the way they once were. Not in steel, not yet, maybe never, but on paper the path exists, and paper in the long arc of human technology has a way of eventually becoming steel.